Hello my friends, this is lecture 5, electric torque on charges. So mainly we'll look at electric torque. As we remember from our previous classes, torque is defined as, very shortly, the rotational effect of forces. Not only, it doesn't have to be a force. Rotational effect of forces. We know when we put charges in the electric field, they are applied a force. Positive charge is pushed in the same direction as the electric field, and negative charge is pushed in the opposite direction, as we see in this figure here. So if we put a charge in electric field, it will be applied a force. This is something we know. This is a nice example here. We have an electron in the air, and the Earth's electric field is about 100 Newton per Coulomb. What is the acceleration of this electron? This is just a review of force. Electric force on a charge is equal to charge times that electric force, so QE. Charge here is electron charge, and we find that force, electric force on that electron, it's upward, and it will accelerate upward. It will overcome the gravitational force, so we are ignoring that. And the acceleration will be from F net is equal ma. A is equal to force divided by the mass, and we'll get a very large acceleration, which makes sense. There will be a force question. If we put any charge in electric field, we know it's applied a force. This is also reviewing the force here. A proton is moving to the right in a vertical field, so I assume I throw this proton in here to the right. It has a velocity initially. What will be its velocity? A short time later, we know there will be a force upward in the same direction as electric field. Yes, it's QE, but we don't have to calculate it in this case. What will happen is that this proton will be pushed upward a little bit, so it will be given a little bit of velocity upward. Let me draw that here. So this velocity will be added here, a small velocity, and over the time it will increase. It will be moving more and more, rotating more and more upward, but a short time later it will have a velocity about this direction, so our answer would be C here. A very cool application of electric forces. Here we charge DNAs, and the charged DNA samples are put in a viscous fluid. So there is a drag in the viscous fluid, and an electric field is applied. As you see here, there is a plus plate and minus plate. This is actually a parallel plate capacitor. So there will be an electric field from left to right. I'll draw one for symbolically, maybe several more. We know that there is an equal electric field. So as we draw the electric field lines, we try to draw them equally separated, although this is hard. And if DNAs are charged negatively, they will be pushed in the opposite direction to the electric field, as shown here. What happens here is that if there are two samples of same DNAs, same DNA, same mass, and so on, same size, they will have same net force, same drag forces, and electric force is the same. So they will, an electric force, and they will move with the same velocity and same distance, and we can find if two DNAs are the same. This is a very, very cool application of electric forces. As we come to the torques, for a dipole in electric field, we put a dipole in electric field. There isn't much confusion here. All we have to do is draw the forces applied to plus and minus charges. Here we have an electric field upward, so force on plus charge will be upward and minus charge will be downward. We have the same charges, same amount, different charge sign, but same amount of charge, so the forces will be the same. Writing down the force is equal to QE. So same strength of forces, one is up, one is down, total force is 0. We can call that F net, or total F. The sigma symbol is for total F is 0. But we have a torque, since the plus is pushed upward, minus is pushed downward, we'll have an overall rotation, and this we can understand by logic. This rotation will continue until these forces cannot rotate our dipole anymore, and as we can see here, as the dipole aligns with E, let me spell that correctly. As the dipole aligns with E, there will be no more rotation because the force is up and down still, but they can't cause rotation. There is no rotational effect. So what we say is total net force, or total force, is 0, but net torque or total torque is not 0 here. In first two pictures here, torque is also 0, right? Because there's no rotational effect. That's simply what we're going to look at here. We'll look at logical applications and so on. We won't be really doing comprehensive calculations. One very cool application of electric torque is how we heat food in a microwave. There is water in everything, water in food, and water is an electric dipole. H2O is a natural dipole. So we have hydrogens here, oxygen there, and hydrogens are plus. Generally oxygens are negatives because electrons spend more time in oxygens. This is a detail, you don't have to know that. Electrons spend more time, so this side is more negative. So we have a dipole overall upward directed, plus to minus. And what happens when the electromagnetic wave comes, we call these EMG waves. Microwave is an electromagnetic wave. We'll get to there. And how electromagnetic waves works is that electric field keeps changing direction. It's up, then it rotates, becomes down, and then rotates back, becomes up, and so on. As it does that, the dipole keeps rotating because it applies different force, the same force in different directions. So applies F is equal to QE in different directions. So the water dipole will align along electric field, but it will keep realigning because electric field direction keeps changing. And as a result, what happens is molecules keeps moving. They become hotter and hotter because they gain thermal energy, and we have hot food. So this motion conversion gives them a thermal energy and heats our food. Isn't that cool? Some questions here. We have a dipole. This is electric field. Which of the following describes the subsequent motion? We look at forces. That's all we do. Logically, positive will be pushed along the electric field. We have same amount of charges, so forces are magnitude is the same. Negative will be pushed in the opposite direction, so forces cancels. No net force. There's not also a rotational effect here. We can easily see that the dipole will stretch maybe a little bit, but it will not rotate. So it will remain motionless. This question here, which of these dipoles has a zero net force or no net force? Answer is all of them, because up F and down F, same charges, plus minus, they'll have zero force. And the same here, and same in this case. See, so all of them has, this one is actually down and up. All of them has zero net charge, net force, not net charge. So all three dipoles has zero net force. If we think about the net torque though, all of them will be able to rotate. A will rotate clockwise. If I imagine that logically, imagine you put your pen and you're pushing it like so, it will be rotating clockwise. B is the same, clockwise rotation. Total force is zero, but total torque is not. But C is actually pushed inward from up and down, so it won't be rotating. Zero rotation, zero torque. That's the general idea here.